Hi guys, welcome back to SEM 3. This is our week 1 content, thermochemistry Born-Haber cycle. Now before we go into Born-Haber cycles, we need to recap on certain definitions that we learned in SEM 1. Examples, we have lattice energy. What is that lattice energy? We have enthalpy change of atomizations, and we have enthalpy change of formations, combustions, solutions. All these definitions are important, okay? So the first things we look at, what is lattice energy? Now lattice energy basically is the energy required to break the ionic bonds between ions in an ionic lattice structure. Now what is that ionic lattice structure? Let's say for example when NaCl arranged in a solid state, we have sodium plus, Cl minus, sodium plus, Cl minus, Na plus, Cl minus, Na plus, Cl minus. Now they arrange in an alternate manner between oppositely charged ions. Now this is how they attract to each other, by ionic bonds. So the blue indicates the ionic bonds between ions. So therefore ionic lattice structure will have a strong ionic bond with high melting and boiling points. Okay, so now since we are talking about lattice energy, it is the energy need to break this bond, okay, to separate the oppositely charged ions apart and changing them into a separate gaseous ions like that. So you are basically changing a solid sodium chloride into individual sodium and chloride ions. And of course they are in the gaseous state, they should be in random motions. Alright, so in this process, while we change from solid into gaseous ions, we need the energy to break the ionic attractions. And this energy, we call it as lattice energy. Okay, so let's ask you a question here. Would they be exothermic or endothermic? Of course, we learned about exo and endo, right? So endothermic is absorbing heat, endothermic is releasing heat. Basically, breaking bond is endo, forming bond is exo. Now obviously in this case from a solid into gaseous, meaning that we are breaking bonds, so it's always endothermic. So the enthalpy change of lattice energy, hope you still remember this symbol, the triangle with a H, this indicates enthalpy change of lattice energy. So in this case, from solid to gaseous ions, lattice energy is actually a positive ions because, positive energy because they are absorbing heat to break the bonds. So we can look at this reaction in the reverse directions where we can change sodium gaseous ions and chloride gaseous ions back into the solid. Okay, so from these we combine them and then they arrange in a NaCl lattice structure like just now, so going backwards. So what do we call this? Obviously this also known as lattice energy, okay, but the sign will be the opposite, which is negative. All right, so one is absorbing heat to break the bonds to break down an ionic solid, another one is to combine the gaseous ions to form 1 mole of ionic solids, both known as lattice energy. Now how can we differentiate them rather than just looking at the sign? So without sign given, if I just put you lattice energy, you wouldn't know whether this is breaking a solid or forming a solid, right? So another way to identify them, sometimes they call it as lattice breaking, which is this, you're breaking a solid. And another one, sometimes they call it as lattice formations, means you're forming 1 mole of ionic solid. So don't be surprised when you see lattice energy with positive and negative signs, or lattice energy named as lattice formations or lattice breaking. All right, so this is lattice energy. Now, what are the factors that are affecting lattice energy? How can we actually determine the strength of the lattice energy? How high is that? All right, so let me erase that. Okay, let's continue. Now, factors affecting lattice energy, we have two. Number one, we should consider ionic charges because we are dealing with ionic compounds. Next, we're talking about ionic radius. All right, how ionic charges actually affects the lattice energy. Number one, when the ionic charge is higher, the higher the charge, the stronger the bond. So lattice energy will be higher. Now, higher in this case, it can be positive or negative. It can be exo or endo. All right, it can be more exo when you're actually forming a stronger ionic compounds, or it can be more endo when you're trying to break a strong ionic compound. So when ionic charge increases, lattice energy increases. Okay, be it positive or negative, exo or endo, depends on whether you're breaking or you're forming a solid. Now, ionic radius. What about ionic radius? What do you think? Now, let's say I have a comparison between sodium ions and magnesium ions. All right, and then we have chlorides here, chlorides here. Let's make a comparison. In terms of ionic charge first, it's very obvious here, sodium is positive, magnesium is 2 positive. So which means the ionic charge of magnesium is higher than sodium. Hence, magnesium chloride will have higher lattice energy as compared to sodium chloride. Okay, now what if we are comparing in terms of ionic radius? Let's say not magnesium 2 plus, but I change it to potassium plus with chlorides. So what do you think comparing between sodium and potassium? Now, since chlorides are the same, so we're just comparing between sodium and potassium. Now, both from the same group, and knowing that potassium is much bigger in terms of ionic radius compared to sodium, so which one will have a stronger attraction? Of course, the one with the smaller radius, the nucleus is actually closer to the surrounding, including the negatively charged chloride. So the attraction towards the negatively charged ion is stronger. All right, compared to the one with the bigger radius, the nucleus is further away from the surrounding, so the attractions in a way is actually weaker towards the chloride ions. So in this case, I can say when ionic radius is smaller, lattice energy will be higher. So a conclusion is ionic charges is higher, ionic radius is smaller, both making lattice energy greater. All right, so this is about lattice energy. Why is it so important about lattice energy? And I spend so much time on this because later when we go into Born-Haber cycle, we need to understand the whole process. And it's all about lattice energy because we are going to form an ionic solid. All right, so let's go into Born-Haber cycle. Now, what is that Born-Haber cycle? It's a cycle just like Haber's law that we learned in Sem 1. Okay, it's a cycle that involves a lot of arrows and a lot of energy involved. So Born-Haber cycle gives the relationship between enthalpy change of formations. Like I said, they are forming 1 mole of ionic solid, and also the enthalpy changes in 5 stages of the formations. So what are the 5 stages of formations? See, if I give you a formations equation, let's say I want to form 1 mole of sodium chloride. So according to definitions, 1 mole of sodium chloride formed from its element. So sodium solid from the elemental state plus chlorine gas form 1 mole of sodium chloride solid. Now that's enthalpy change of formations, which is what they meant here. Okay, so this is the formation equation. Of course, we need to balance it, half. Now, don't ever multiply by 2. I know multiply by 2 is the same thing. It's still balance the equation, but just that you're not actually forming 1 mole of solid. So according to definition, you should get only 1 mole of solid. So please adhere to the definitions. Now, this is formation equations. Now, what are the 5 stages? Look at that. Imagine you're in the lab now. I give you sodium metal and a chlorine gas, and you try to put them into the same beaker or into the same gas jar. Like I have a gas jar full with chlorine gas, and I drop 1 piece of sodium metal into it. Do you expect, boom, straight away you get sodium chloride, which is kitchen salt? No, right? So this wouldn't happen. I mean, this is not a magic, right? So this wouldn't happen. Now, they happen by stages. It's not like a magic. You mix them, boom, you get a sodium chloride solid. Now, what are the stages involved? First, okay, the first stage is from the elemental state, they will change slowly accordingly. So first, sodium solid will be atomized. So it involves atomization. Same goes to the chlorine gas, atomization. Now, what is that atomization? Atomization is breaking down an elemental solid or gas, as long as it's elemental state. So they break it down into gaseous atom. So sodium solid, it changed into sodium gas atom, and then chlorine molecule. See that? Cl2. It breaks down into chlorine atoms in the gaseous state. No more Cl2 because it's half Cl2. So yes, it's balanced. Now even from here, you need to balance it. All right. So now both change into gaseous atom. This is atomization. All right. Once you have atomized them, then you start ionizing them. So for sodium, you ionize it into sodium positive charge, ionization energy. Right? And then chlorine remain unchanged here, chlorine gas, still the same. Next, I'm going to change chlorine into chloride. Again, I try to ionize it, but we don't call it as ionization because ionization is changing it into a positive ions. All right, ionization is changing to positive ions. So in this case, if you want to change it into negatively charged ions, we call that as electron affinity. All right, that's electron affinity. So we are changing sodium, the same, no change because it's already ions. We're changing chlorine atoms into chloride ions. All right, now both change into gaseous ions. What happened next is from the gaseous ions, you can combine them to get sodium chloride solid. Like what I explained just now, this is actually lattice formations, or we just call it as lattice energy. You're forming 1 mole of ionic solid. Now this is the full Born-Haber cycle. Now how many stages we have here? Atomization 1 stage, ionization, electron affinity. Because atomization, they split it into 2. One is atomizing the sodium, another one is atomizing the chlorine. So 1, 2, 3, 4, 5, including the lattice energy. So in total, there are 5 stages. All right, in forming 1 mole of sodium chloride solid. Now, I'm not sure whether you noticed that some arrow is pointing upwards, some arrow is pointing downwards, right? Enthalpy change of formation is pointing horizontal because formation can be positive endothermic or negative exothermic. Now, if I point an arrow upwards, meaning that this is an endothermic reaction. Does it make sense? Atomization means you're breaking down the solid into gaseous atom. You're breaking down the molecules into individual atoms. So we are absorbing heat to break it down. So it's always endothermic. Same goes to ionization energy. We are breaking the attractions between nucleus and the outer electrons by removing 1 electrons from sodium to get sodium ions. So it's positive. But then for electron affinity, the arrow is pointing downwards, which indicates that this is actually a negative value, which is exothermic. Now, why is it exothermic for electron affinity? You're trying to put in an electrons, right? Let's say I have chlorine atoms, which is neutral, balanced in terms of protons and neutrons, and also electrons. All right, they're balanced. That's why it's neutral. Now, I'm forcing 1 electrons. I force to put in 1 electrons into it. So what happened? You're forcing them to form a new attractions between the nucleus and the additional electrons. So you're forming bond between the nucleus with an additional electron so that you get Cl minus. So here is an exothermic reaction because you're forming bond. So heat release. So the total, the difference between all the endothermic and the exothermic, including the lattice forming here, which is exo, you get the total Born-Haber cycle. Or you can get the total energy called lattice formations. Now, the equation is something like that. This is the full Born-Haber cycle. Enthalpy change of formations is equivalent to the addition of the sum of all this. Okay, atomizations for both sodium and chlorine, plus with ionization energy, plus with electron affinity, right? And plus with lattice, plus with lattice energy. I'm using short form here. All right. So basically you're adding up everything here. This, plus with this, plus with this, plus with this. Bear in mind these two will be in negatively charged, negatively signed. So when you add up everything, you get the total energy called the enthalpy change of formations for the formations of 1 mole of solid. Now this is Born-Haber cycle. Okay, so let's check it out, an example here. So calculate the electron affinity of fluorine given the following information for the formation of sodium chloride. Now, they give you all the data here. We have atomization of sodium, we have atomizations of fluorine, first IE of sodium, which we can check it from data booklet. Lattice energy of sodium fluoride, yes, it's given. See that? It's negative, means this is actually lattice formation. Okay, you're forming 1 more of solid, lattice formations. And then enthalpy change of formation sodium fluoride, you get the formations values, which is this. Now, the only one missing from the Born-Haber cycle is actually the electron affinity of fluorine. So making use of the equation just now and the full Born-Haber cycle, you can get the electron affinity of fluorine. Okay, let me show you that. Okay, I try to construct it here in the smaller versions. So I always start with enthalpy change of formation. In this case, it's sodium fluoride. So sodium solid plus with fluorine gas, you get sodium fluoride solid. Bear in mind, you have to balance them and make sure it's 1 mole of solid. That's the first stage. All right. And the next stage is we atomize them. So from here, you atomize both together, and they're both separate value, so make sure you pay attention to that. Atomization of sodium is, let's check it out, 107, so 107 positive. Atomization of fluorine is 79 plus 79 here. So we change them into sodium, no longer solid but gas. Fluorine is a molecule, suppose, now is a fluorine atom. Half times 2, you get 1. So that's a balance equation. Alright, next we atomize them. After that, we ionize it. So ionization energy, what is the value for ionization of sodium? It's given here, positive 496. All right, so you change it into sodium plus gas. And next, we still maintain fluorine as a gas. We change it step by step. After that, we know that electron affinity, what we want, but we know is always exothermic. So we write it out, sodium plus gas plus fluorine minus, which is fluoride. And here is the X value. Now, you don't have to put in the negative charge. All right, X is just an unknown. So later when we substitute it into the equations, which I will show you later, then automatically you will definitely get a negative ions, negative value. Negative ions, I always mention that. Okay, so after that, we have sodium and fluoride ions in gaseous state. So we combine both. Last stage will be always, see that, lattice energy. What is the value? Negative 928. Now we have the full Born-Haber cycle here, and we have all the value except for, sorry, I forgot to put in, enthalpy change of formation is negative 574. Now let's do the calculations, putting it into the equations. So what is the equation again? Enthalpy change of formation, which is negative 574, equivalent to the additions of everything, right? So positive 107 plus 79 plus 496, see that, ionization, and then plus X, which is the electron affinity, and then minus, plus negative 928. All right, now from here you will get the answer. All right, let me do the quick calculations here. 107 plus 79 plus 496 plus, sorry, minus 928, and then negative 574 minus the answer. Negative 328. Okay, so let me double check again. Just now was negative 574 minus 107 minus 79 minus 496 and then plus with 928. Yeah, negative 328. All right, so this is the answer. Of course, this is energy, so it's always kilojoule per mole. Yep, that's it. So this is the X value, where we call it as electron affinity of fluorine. And it makes sense when you get a negative. If you get a positive, you have to recheck your calculations again. Now, that's it. This is how we construct a bond-Haber cycle and calculate whatever unknowns that made it for us to calculate. All right. So I hope this video is clear enough, and it's not too long to explain about lattice energy and bond-Haber cycle. I'll keep an example in the OL page, so you can try that out and see where you get the answer, and if we do a further discussions in the tutorial. All right. Thank you.